Hey everyone, it's Dr. Marcon. This is part 4 of our cardiovascular physiology lecture series. We're going to be talking about flow, pressure, and resistance with regards to blood and the heart. Flow rate is dictated by pressure differences. Pressure we can define as the force exerted by a fluid on the container holding that fluid. So we looked at pressure differences in the different chambers of the heart, and we know that flow of blood goes from an area of high pressure to low pressure. So for example, during systole, we know that the right atrium or right atrial pressure exerts a pressure of 5. And then during systole, we have an increased pressure or a greater pressure in the right atrium compared to the right ventricle. So if the right atrium is undergoing its own atrial systole, meaning having a pressure of about 5, in the ventricle the pressure is at 0, so allowing for filling of the ventricle of blood from the right atrium to the right ventricle. So it's this pressure difference that dictates flow, and we will see that pressure differences also dictate flow in the blood vessels. So blood flow obeys the rules of fluid flow, and flow is directly proportional to the pressure gradient between 2 points and inversely proportional to the resistance of the vessels to flow. So if we have an increase in the pressure gradient, we'll have an increase in flow. However, if we have an increase in the resistance of the vessels, this decreases flow. If you look at your book in chapter 15, table 15.1 actually enumerates the rules of pressure, flow, and resistance. In the cardiovascular system, starting off with the formula. Flow equals the change of pressure or the pressure gradient over the resistance. So I can write that. So flow, we're going to say Q represents flow, and we'll get into those different variables in just a little bit. So flow, Q, equals the change in P, or pressure, and the pressure gradient, divided by the resistance. Okay, so by this formula we can see that flow is directly proportionate to the change in pressure or the pressure gradient. So an increase in the pressure gradient causes an increase in flow, whereas it is inversely proportional to resistance. So if you have an increase in resistance, you have a decrease in flow. So the table 15.1 again enumerates the rules governing this formula. So the first rule is blood flows if a pressure gradient, also known as delta P, is present. So delta being the symbol for change. So blood flows if a pressure gradient is present. The second rule is that blood flows from areas of higher pressure to areas of lower pressure. And we saw that with regards to the chambers of the heart. Third is that blood flow is opposed by the resistance of the system, and we'll talk about resistance in just a little bit. The fourth rule is that there are 3 factors that will affect resistance. The first and most important being the radius of the blood vessels, second, the length of the blood vessels, and third, the viscosity or stickiness or thickness of the blood or fluid. Fifth rule, flow is usually expressed in either liters or milliliters per minute. And then the next rule, number 6, velocity of flow is usually expressed in centimeters per minute or millimeters per second. And the 7th rule, the primary determinant of velocity when flow is constant is the total cross-sectional area of the vessels. And we saw that when we discussed blood vessels in the last lecture series. We saw that within the capillaries, it has the largest total cross-sectional area, And we know that this is advantageous because we want to decrease the amount of flow in those areas so that we can have maximal amount of diffusion of nutrients, of gases, whatever. So increasing the cross-sectional area of the vessels determines velocity and flow rate. And we saw that again in the smaller vessels, specifically the capillaries. So this picture just shows pressure differences in millimeters mercury. We can see that flow rate is, again, dictated by pressure differences. So for example, we might have different flow rates, but we see that despite, one end being 100 millimeters mercury and then another end being 75 millimeters mercury, the pressure difference or the change is only 25. Same with the bottom, the flow may only be 40 millimeters mercury, and here we have 15. Again, the change in pressure is only 25. So that being said, the flow is equal. So there might be a difference in pressure, the difference in pressure is same in both vessels, showing that the flow will also be equal in both vessels. And we know that pressure gradient is a more important variable for flow. This slide just shows the general formula and how we use flow in terms of the other variables. So if we kind of rearrange the other formula, we can see that pressure can equal flow times resistance. So pressure symbolized by a big letter P, and in this case we're talking about changes in pressure or the pressure gradient, equals flow Q, because we can't use F, F is being used for another variable, times resistance big R. So this is actually a pretty easy formula to remember because it's in alphabetical order. Just remember PQR. So pressure equals flow Q times resistance R. So again, pressure equals flow times resistance. And you can do different calculations by manipulating this equation to get the different derivatives. For example, we can find out the formula for flow. We know that flow equals pressure divided by resistance. If you do a little bit of algebra and kind of manipulate the different variables, we can get formulas for flow and formulas for resistance as well. So vessel diameter actually is what contributes the most to resistance. Resistance, again, according to that table 15.1, depends on three important factors. So resistance R will depend on tube length, represented by capital letter L. If we have an increase in length, we'll have an increase in resistance. The longer the tube, the greater the resistance, because you have more of a chance of the fluid to come in contact with the inside of a tube, and the friction inside the tube will decrease flow. So we can see this long tube will increase the amount of resistance. Another variable that we talk about with regards to resistance is fluid viscosity. Viscosity, again, being that thickness or stickiness of a fluid. So fluid viscosity is represented by this weird N, and we know that an increase in viscosity will also increase resistance. So for example, if you're drinking through a straw of the same length, and there's a difference between drinking a thick milkshake versus drinking water or soda. It takes a lot more strength to drink a nice thick milkshake versus drinking just a less viscous fluid such as soda or water. A third variable that will have an effect on resistance is the tube radius, and this variable actually is what has most of an effect on resistance. So we know that tube radius increases, any increase in tube radius would decrease resistance. So they are inversely proportional. So again, an increase in radius would cause a decrease in resistance. So we plug in these variables into a formula, and it was actually the Frenchman Poussy that put these variables into law with regards to resistance. So the first equation we see here on the left shows Poussy's law, where resistance, R, to blood flow is directly proportional to the length of the tube through which the blood flows, so length L, and the viscosity of the fluid, the thickness or stickiness of the fluid. So any increases in length or viscosity will increase resistance. The bottom part of this formula shows the relationship of the radius of a tube with resistance. So we know that resistance is inversely proportional to the radius of the tube to the fourth power. So it's this radius that actually has more of an effect on resistance compared to the other two variables. So we can actually plug in this formula, Poussy's law, into our formula for flow. We know that flow Q equals the changes in pressure divided by the resistance. So when we plug Poussy's law into the formula for flow, we get the equation on the right here. So flow being directly proportional to the change in pressure times the radius of the tube to the fourth power. So any increase is in the change in pressure or any increases in the radius will cause an increase of flow. And then we can see that flow is indirectly proportional to the length as well as the viscosity of the fluid. So any increases in the length or any increases in the viscosity will decrease flow. Okay, so we can see how we can plug resistance into our formula for flow. And our original formula being Q equals change in P, or the pressure gradient divided by the resistance R. And Poussy's law gives us the formula for resistance here. Now, tube length changes very little in humans. Once we become adults, the length of our tubes don't really change too much. So it doesn't have too much of an effect in terms of resistance. Fluid viscosity changes are slow. So we have disease conditions that could cause fluid changes in fluid viscosity, such as we talked about polycythemia, where we have an increase in the number of cells, which increases velocity. We can have increases in the amount of proteins, or we could have dehydration, where also changing fluid viscosity. But again, these changes are slow and can cause slow changes in resistance. However, we can see that tube radius will have more of a major effect on resistance. We change tube radius very quickly with sympathetic signals, which change tone, hormonal changes, as well as local factors that we talked about that can cause vasodilation and thus increasing or causing immediate changes in the tube radius and resistance. Now, small changes in radius have significant effects on resistance. We can see that it's R to the fourth power. So, for example, if we increase the radius to 2, the radius would be R to the fourth, so to the fourth power. So 2 times 2 times 2 times 2, that equals 16. So let me write R to the 4, R to the fourth. And if we change R to 2, we can see that R to the fourth would be 2 times 2 times 2 times 2. And that equals 16. So that means we'll have a 16 times increase in the radius. And, you know, because we know that the radius is inversely proportionate to resistance. If we have a 16 times increase in radius, we'll have a 16 times decrease in resistance. And a decrease in resistance causes a proportionate increase in flow, because we can see flow and resistance are also inversely proportionate to one another. So this is huge. Small changes have significant effects due to this formula. So we know that radius definitely has more of an effect with regards to resistance and thus with regards to flow. So here we see, again, we have our general formula where pressure or changes in pressure or pressure gradient equals flow Q times resistance R. And we can rearrange the different variables in the formula. We can get our flow formula where flow Q equals the pressure or change in pressure or pressure gradient P divided by the resistance R. So if we have the formula Q equals P over R, we know that flow is directly proportionate to pressure. So any increases in pressure, you have an increase in flow. And then flow is inversely proportionate to resistance. So an increase in resistance, you have a decrease in flow, or an increase in resistance, you have an increase in flow. So we're not really talking about the speed or velocity of blood. We are talking about flow, and we measure flow in milliliters per minute using this formula. So flow Q equals P over R. Okay, so flow describes the volume that passes a given point in a given time. Now, hemodynamics is basically looking at how blood moves. And we use those variables of flow, pressure, and resistance to look at how blood moves. So we maintain pressure to maintain flow. And we can hemostatically control pressure in order to control flow. It's easier to measure changes in pressure than to measure changes in flow. So we know that pressure determines flow, and we know that changes in resistance also determines flow. So to change flow, we can either change pressure or change the resistance. However, physically speaking, we cannot change pressure that much because it could cause physiological damage. So, for example, if we want to increase flow by a factor of 10, we would need to do a 10-fold increase in pressure, meaning, for example, if our systolic pressure was 120, we would need to increase systolic pressure from 120 to 1200 to cause a 10-fold increase in flow. And that can cause a lot of damage. That can cause a stroke. It can cause our vessels to virtually explode. So that's why we don't really rely on changes in pressure to change flow. It's not physically possible or advisable, and can cause stress on the system. However, for resistance, there are variables that, affect resistance that we talked about. We talked about length and viscosity. However, for length and viscosity, we can't really change the length of the vessels. Once we reach adult age, the length of our vessels is pretty static. And to change viscosity of blood would be too slow. And we talked about that in earlier slides. So a more practical way to change resistance in order to change flow is to make changes of the radius of blood vessels, and this proves more rapid and more potent, and you can do this at various points within the body. So flow is regularly changed through changes of the radius of the blood vessels. We know that if we have vasoconstriction, we have a decrease in flow. If we have vasodilation, we have an increase in flow. So a decrease in the diameter or the radius of the blood vessels decreases flow, and an increase in the radius will increase flow, as we see in our formula here for flow. So we know that flow is directly proportionate to the size of the radius of the blood vessel. So it's more physically possible to change flow by doing changes of resistance through changes of the radius. And we do that through different ways, through our sympathetic nervous system, through hormonal signals, as well as local changes such as the release of local factors. Pressure differences drive blood flow. Unless specified, we are talking about pressures within the arteries. So we talked about systolic blood pressure is an indication of contraction, and then diastolic blood pressure is an indication of relaxation. We also know that pressure within the arteries is usually greater than the pressure within the veins, allowing for blood to flow from the arteries to the veins. Now this is a graph showing pressure waves created by ventricular contraction traveling into the blood vessels, and we saw this earlier. We can see that pressure in the arterial side of the circulation cycles, and we can see the different pressure waves, but we see that the pressure waves begin to diminish in amplitude with distance, and this is due to friction, as well as the distance from the original pressure wave to when we reach the capillaries. So we can see the pressure waves diminish in amplitude and distance due to friction, and will then disappear in the capillaries. So by the time the blood reaches the veins, the pressure has decreased because of friction, and we can see that a pressure wave no longer exists. We see that venous blood flow is steady rather than pulsatile, pushed by the continuous movement of blood out of the capillaries. So pressure in the artery is greater than pressure in the veins, and we can see and we compare the mean arterial pressure in these different vessels. So within the aorta, for example, we can get the mean arterial pressure from the systolic blood pressure and the diastolic pressure. So we know that mean arterial pressure, which is the average blood pressure over time, is equal to 1/3 of systolic blood pressure plus 2/3 of the diastolic blood pressure. However, we can also use a more simpler formula using pulse pressure. Pulse pressure equals systolic blood pressure minus diastolic blood pressure. So the formula we can use to make things a lot more simple for mean arterial pressure is MAP equals 1/3 the pulse pressure plus the diastolic pressure. So let's write this out. MAP equals 1/3 pulse pressure, which we'll put as PP, plus diastolic blood pressure. Diastolic blood pressure. Okay, so if we, for example, we know that we have our systolic blood pressure in the aorta, for example, is 120 millimeters mercury, and diastolic blood pressure is 80. So 120 minus 80 equals 40. So the pulse pressure in the aorta is 40, and then we would get 1/3 of 40. So 1/3 of 40 we would calculate to be about 13.3. So 13.3. And then we just add the diastolic blood pressure, which is 80. And that will give us our mean arterial pressure of 93.3. Okay, it's the same way of getting the mean arterial pressure if we take the 1/3 of the systolic plus the 2/3 of the diastolic. Again, that representing the amount of time that the heart is either in systole versus diastole. We know that the heart is contracting or in systole 1/3 of the time, and it's in diastole or relaxation in 2/3 of the time. So using this formula, mean arterial pressure equals 1/3 pulse pressure plus diastolic blood pressure is a simpler formula to get mean arterial pressure. We also know that pulse pressure measures the strength of the pressure wave, and it's also a good indication of stroke volume. So the higher the pulse pressure, the higher the stroke volume. And we'll talk about stroke volume in the next slide. So these formulas basically are a way of showing ventricular performance or the effectiveness of the heart as a pump. Stroke volume, basically this is the volume that's pumped per contraction, and it is estimated by the pulse pressure. So stroke volume in earlier formulas we saw equals end diastolic volume minus end systolic volume. So the amount of volume of blood at the end of diastole minus the end volume of blood at the end of systole. Okay, and we can estimate stroke volume by pulse pressure. So pulse pressure equals systolic blood pressure minus diastolic blood pressure. The next formula that we want to take a look at is ejection fraction. So this is how much blood is ejected as a percentage. And we know that average ejection fraction is about 70%. We talked about values earlier, so we know that we can estimate end diastolic volume to be about 100 milliliters, and we know that stroke volume is regulated to be about 70 milliliters. So if we take stroke volume divided by end diastolic volume, so 70 divided by 100 milliliters, and we multiply that by 100, we get about 70%. So 70% being normal ejection fraction. That's the amount or percentage of blood that is normally ejected. Cardiac output is the volume of blood pumped per minute. We know that cardiac output, the formula for that is stroke volume times heart rate. And we can calculate cardiac output during 3 different conditions. Here we can see at rest. At rest, our heart rate can be about 70 milliliters per beat, or 70 beats per minute. If we take the formula cardiac output equals stroke volume times heart rate, stroke volume in this case being 70 milliliters per beat, multiplying that by the heart rate, we get approximately 5 liters per minute for the cardiac output. For exercise, we have an increase in the amount of stroke volume, or the amount of volume blood pumped per contraction. So with exercise, we could have 150 milliliters pumped per beat, and our heart rate can go up to 200 beats per minute. We get that blood flowing, lots of exercise. So we can calculate the cardiac output to be about 30 liters per minute. Now, in a cardiac patient, if we see that their heart rate has decreased, we can see that stroke volume is about 25 milliliters per beat. They have 40 beats per minute for their heart rate, which is showing bradycardia. Using our formula again, the cardiac output we can estimate to be about 1 liter per minute. Okay, so we can use this formula to estimate the volume of blood pumped per minute. And we know that cardiac output can vary significantly. So we know that flow is the same as cardiac output. If we we can also use that information to kind of plug into our mean arterial pressure formula. But first we have to accept that flow Q is the same as cardiac output. So how much blood is being pumped by the heart out into the system is equal to flow, or the flow of blood. Resistance, R, we're going to say is the same as total peripheral resistance. So peripheral resistance is just the resistance to flow by the arterioles. And we have already used this formula. Pressure is equal to flow Q times resistance, big R. Now, using that information, we can then derive another formula. We know that mean arterial pressure is equal to cardiac output times total peripheral resistance. So cardiac output, again, being the same as flow, resistance being the same as total peripheral resistance, okay? And we also know the previous formula for cardiac output. Cardiac output equals stroke volume times heart rate. So based on that information, we can say that mean arterial pressure equals stroke volume times heart rate times total peripheral resistance. Under the condition of exercise, for example, if we have an increase in cardiac output due to an increase in stroke volume and heart rate, if we have a decrease in total peripheral resistance, this will not affect the mean arterial pressure, because while we are increasing cardiac output, meaning the flow of blood into the arteries, while decreasing total peripheral resistance, allowing more blood to flow, this will not affect mean arterial pressure. So the two formulas that we need to look at that you should know and understand is mean arterial pressure equals cardiac output times total peripheral resistance, as well as mean arterial pressure equals stroke volume times heart rate, which is the same formula for cardiac output, times total peripheral resistance. So make sure you know and understand these formulas. Mean arterial pressure, again, is the average blood pressure over time. We see a decrease through the system because of an increase in resistance. We know that mean arterial pressure is also homeostatically regulated via stroke volume, heart rate, as well as total peripheral resistance, which we can estimate using Poiseuille's law. And so, one of the most important equations that we do is this equation right here. Mean arterial pressure equals stroke volume times heart rate times total peripheral resistance. And then we will talk about homeostatic regulations in the next lecture.